Hi everyone, here are your notes for lesson 3. Today we're going to be getting into properties of logarithmic functions. So the reason why we need these properties is as we continue further and getting into logarithmic and exponential equations, you're going to want to have these properties on hand. So for any positive numbers, we're going to use m and n as our values of our positive numbers. And b, where b cannot equal 1, so b is still going to be our base. And p, which can be any real number, the following properties apply. So we have 3 different properties that are there for logarithms. The first one is what we call the product property. And what the product property says is that if you have a singular log with any given base, that's not equal to 1, right? And you have the product of 2 things. So I'm going to say m and n, or I guess it would just be written as mn, right? I can expand that into multiplication, and so into 2 logarithms with the same bases is the sum of log base b of the first factor, which is m, plus log base b of n. So I can expand and condense. I can work left to right and right to left, depending on if I'm expanding or condensing. So if I have log base b of, let's say, m, n, and q, then it would be log base b of m plus log base b of n plus log base b of q. Right? So we can expand it out into as many sums of terms as you can. The quotient property, so we just did the product, would be if you were to have 2 things being divided, I can expand that out into 2 logarithms, which would be the difference of those 2. And here it is important. Order does matter when we're subtracting, right? So your numerator needs to be the first log, your denominator needs to be the second log. And then the third property that we have is what we call the power property. So if I had log base b of m to some exponent p, what this property says is we can take that exponent of p and put it out in front as a coefficient of the log. So log base b of m. Okay, so product property, quotient property, power property. You're going to get those in your head. Technically, I would say get them memorized, but you don't really have to since you have your notes in front of you. But it would make life easier if you did have them memorized because it just would be a lot quicker. You know that you need to get through your assessments as quickly as you can. So these are all valid for base 10 and base e's, right? So if my base was a 10 or my base was an e. So expanding. So now here we're going to go from a singular logarithm and we're going to expand it out into multiple logarithms. So for a, I have only products here, right? Because isn't this the same as 8 times x times y to the 4th? So since I have a product of 3 different factors, I'm going to expand this into 3 different logarithms. My base is 10. Remember, if there's an invisible base there, it's 10. That's our common log. So I'm going to rewrite this as log base 10, which nothing there, 8 plus log of x plus log of y to the 4th. So now the only other thing I can do is I can take care of this part right here using my power property, which brings that 4 out in front. So it'd be 4 log y, and just bring down the rest. So log x plus log 8. I would look at that log 8 to see if I could turn that into a number. It's not a nice number. 10 to some number is not going to get me to 8. Like if that was log 10, then that would be 1, right? Or if it was log 1, that would be 0. So there could be a possibility that this could actually go to a number, evaluate to a number, but in this case it doesn't. So that's your final answer. Over here in B, we have a division, so I know I'm going to have a subtraction. What's going to be subtracted? Well, my ln of x. So I know I'm going to have a minus ln of x, but what's happening in front? Well, in my numerator I have an ln. I'm going to rewrite this as x squared plus 5 to the 1/2, right? Minus my ln of x. And then what else can I do? I can bring that 1/2 in front, so 1/2 ln, and I can't separate that x squared plus 5. That stays together. It would be different if it was 5x squared. Then I could separate that into an ln of 5 and an ln of x squared. I'll show you what that would look like there in a second. So here's our answer to this one. If this problem was, let me give myself some white space here. Let's switch it up a little bit and make it a little bit different. If this problem originally was, don't write this, just watch, the square root of 5x squared all over x, then we could make that go to 1/2 of ln of 5x squared minus the ln of x, and then that would be 1/2 ln of 5 plus the ln, well, 2 ln of x, right, minus my ln of x. And I need to make sure I keep that 1/2 in brackets in front so that it distributes to both of those natural logs. All right, so just a little food for thought. Now we're going to condense. Now we're going to do the reverse. So now we're going to take everything to a singular log. And sometimes students won't write a singular log. They'll condense it, but then have multiple logs in there. So just make sure you always write one log or one natural log. So if we look at A, I've got a subtraction. So that means we're going to have a quotient. So I'm going to have x to the 5th in my numerator. I'm going to have x, y. I'm going to bring that 2 up top. And I'm going to just ignore the ln for now. Technically, my ln's kind of sitting right here. But let's go ahead and simplify this quotient. So that goes to x to the 5th over x squared y squared. Subtract my exponents on the x would get me x to the 3rd over y squared. And then so it would be the natural log of x to the 3rd all over y squared. For b, this one's a nice easy one. That would just be log of 5 over x. Put parentheses around it, just kind of group it together. C, I've got an addition, so that means I'm going to be multiplying. What am I multiplying? Well, first I'm going to do my power here. I'm going to take that 3 in front. So I have an ln of x to the 3rd, y to the 3rd, times, take this power up, yz squared squared. Is everybody okay with that move? So now I'm just going to focus here and simplify. So that gets me x to the 9th, y to the 3rd, times y squared, z to the 4th. Combining my y's gets me x to the 9th, y to the 5th, z to the 4th. Parentheses around to group it together, and I get my ln. There it be. Okay, so it's just practicing those properties. All right, so now when we go to evaluate logarithms, we have what's called the change of base formula, because on our calculator, well, our calculator does do other bases, and I will show you how it does that too, but maybe you don't have a fancy calculator that does it. I don't know, the TI-84s do. I don't know about the TI-80. I don't think the 83s do. But anyway, so we have what's called the change of base formula that we can use to evaluate any logarithm. So what the change of base formula says is that for any positive real number of a, b, and x, with a not equaling 0 and b not equaling 1, you can have any log with any base of x, and you can change it into a quotient of 2 logs of some given base. I'm going to make that a, where you have log base a of x and log base a of b. So this is the way I remember it. Your base of your original log goes down to the basement, right? So your base goes to the basement right here. And then the number, your input, your x, is going to your numerator. So why do I care about that? Well, here my base is an a. But what I could do is I could make my base be a base of 10 because my calculator has a button for log base 10. We'll talk about that. So what I could do is I could just do log of x over log of b on my calculator. Or I could take it to a base of e, which is your natural log, where I could just do something like the natural log of x over the natural log of b. Okay, so what does this look like on our calculator? If I wanted to evaluate log base 3 of 13, and if I wanted to use, let's say, common log, so using the common log first, and I'll show you that we get the same thing, so you can just kind of pick which one you want. If I do a common log with which is a base of 10, I'm going to do, so log base 3 of 13 Change of base means I'm going to do log of 13 over the log of 3 on my calculator. So I'm going to go ahead and pull up my calculator. Where are you? There you are. Okay, so if I do, so log base 3 of 13, so I'm going to do a log of 13, close it, divide it by a log of 3, hit enter, and I get about 2.335. So approximately 2.335. I could get the same answer if I did a base of e, right? So I'm just going to write this out for your own purposes. So I could do it with a natural log too. So if I do the natural log of 13 divided by the natural log of 3, I'm going to get that same 2.335. Okay, so it doesn't matter what you move the base to, as long as you do the change of base formula correctly and you put your base in the basement, you're going to get the same number. The reason why we're picking common log or natural log is because that's what the buttons are on my calculator. Now, if you do have a fancy calculator, and you go to math, I have to remember where it is. Yeah, down here at the bottom. I have a log base option on my calculator. You might want to see if yours does. And then you just kind of like put it in there. Log 313. It's the cheat. The cheat way for your calculator to do it for you. If you have an 83, I don't think you have that. There could be a potential that your specific 84 might not have that button. And I went to the math and I hit the up to get to the bottom. And then you have your log base. So you might want to see if you have it there. If not, it's not a big deal to do change of base. Change of base is very, very easy. So if I wanted to do part B, I could do a log of 10 divided by log of 6 on my calculator. So log of... Oops, log of, what it's 10 over 6. Log of 10 divided by log of 6, which gets you 1.285. So let's bring that back. Now I forget what it was. 1.285. 1.285. And then if you did a log of 2 divided by log of 1/2, that should get you to -1 if you type it into your calculator. Or do the natural log. I should do natural log. That's less writing, less letters. But I just usually go to common log. Okay, so change of base. Make sure that you can evaluate logarithmics on your calculator. Okay, so let's go ahead and finish up with some logarithmic functions. Now we talked about the graphs of logarithmic functions a little bit last class. So now we're just going to dive into it a little bit deeper. So if I wanted to graph any logarithmic function with a base of b to the x, where b has to be greater than 1, we know that it's the inverse of our exponential, and we know that our exponential, so as long as it's not shifting up or down, has a y-intercept of 0, 1. So your logarithmic is the inverse of it. So that's going to give you an x-intercept of 0, 1. So we are always, always, always going to have that x-intercept of 0, 1. Now what's going to change, depending on the base of your log, is going to be that next ordered pair, right? So we know that we have a vertical asymptote at x equals 0. We know that our graph is going to get closer and closer and closer to negative infinity as it reaches 0 from the right-hand side, and that's a tweak I'm going to be adding in today's notes that we didn't have in last notes. But your second point, or your second ordered pair on that graph is going to be whatever your b is, comma 1. Why? Well, remember, if I had log base b of b, isn't that equal to 1? So log base 6 of 6 is equal to what? Well, 6 to what power is 6? 1, right? So whatever that b is as your x is going to get you 1 as your output. Okay, so our domain is going from 0 to infinity. Our range is all real numbers. It's continuous the whole entire time, and it's increasing on its domain, right? It keeps getting larger and larger and larger. There is no symmetry, so there's neither even nor odd symmetry. We're unbounded. There's no boundedness above or below. We have no extrema, right? And we have no horizontal asymptote. We do have a vertical asymptote at x equals 0, and that may change if we shift. Actually, if we shift left or right, right? So if we move our graph to the left or right, then it's going to change your vertical asymptote. And then our end behavior, I'm going to squeeze that in here. End behavior, you write it where it says end behavior. Oops, behavior would be, so the limit as x approaches 0 is what we did yesterday, but I do want to do a tweak to that. I want to add in, remember when we talked about limits, we put that little plus and minus sign. Do you remember what that meant? That means from which side. So if it was a minus, then we would be coming in from the left side, because our behavior might be different on either sides of the asymptote. So I should have, in yesterday's notes, put the little plus there, because we are only coming in from the right side. So as my graph gets closer and closer to 0, on the right side, what's happening? It's going towards negative infinity. And then the limit as x approaches on my right, I'm going closer and closer and closer to infinity, right? So it's going to infinity. Okay, so there is our end behavior. So what's my end behavior? Is my domain. So what's happening as I get closer and closer to 0? What's happening as I get closer and closer to infinity? Okay. All right, let's talk about all these different graphs. This is the last page, right? Yeah. All right, so describe how to transform the graph. Ooh, these are good ones. Describe how to transform the graph f of x is equal to the natural log into the graph of the given function. So we have a log with a given base. I want to convert it to a natural log. Well, how do we convert logs? We use the change of base, because if I use the change of base formula, I can convert any log into any base, right? So if I do a change of base on this, wouldn't that just go to log of x over log of 5? Well, that would be the change of base on a base of 10, on a common log. Well, can't I just make it into a natural log and have a base of e? Yes. So I have a natural log of x over the natural log of 5. Okay, so there's my conversion for change of base. So now I need to recreate this function as an actual function with natural logs. So I need to figure out what that a is, what that initial number is. So I do know that I need to figure out, right, if I plug in 0 for x, so if I plug in 0 for x, what do I get as my output, right? Because that's going to be my a, my initial. So if I plug in 0 for x, what do I get for my initial starting point? Well, the natural log of 0, the natural log of anything 0, or the log of anything 0 is always 1. So now I have 1 over the natural log of 5 is equal to a. The natural log of 5, I'm just going to do it on my calculator here instead of natural log of 5. So all I'm doing is just typing that in. Gets me some really long funky decimal, so 1.6094 and some change is equal to a. And then solving that for a should get you, so that's going to be what? A, no. Oh, yeah, just do 1 divided by that, right? Yee. So 1 divided by the natural log. I lost my mind for a second. Gets me 0.62133. Which I guess I could have just done 1 divided by the natural log of 5 on my calculator. Yeah, I could have. Okay, so my new function written in natural log form is 0.6213 natural log of x. Okay. So my original function of f of x, so we transform the graph, so we transform our original function f. So f of x, let's say, is here, right? It's at 1, 0. That's a really bad logarithmic graph, but hopefully you can do better. So what's changing? If f of x is the natural log of x, what's changing with our graph? Well, we're doing a vertical shrink, right? Because my a is smaller than, is in between 0 and 1. So it's probably going to look something like this for my g of x. It's going to be a little bit of a shrink. It's not going to be as steep. All right, so let's do the same thing over here. So I have, what's this going to be? So the natural log of x over the natural log of 1/2, which is the same as 1 over the natural log of 1/2, which is equal to a. So 1 divided by the natural log of 0.5 gets my a to be about negative 1.443-ish. So my new function of h of x is equal to negative 1.443 ln of x. So what's changing? So here's our original, right? Here's my f of x, 1, 0. So what's happening? Well, we have a reflection. So we're going to reflect over the, that's going to be the x-axis, right? Because it's in front. If it was attached to the x, it would be over the y-axis. And we have a vertical stretch. Okay, so it's going to look maybe something like this. H of x. Okay, I don't know. Those are really rough sketches, but we'll go with it. Okay. All right, so make sure you can do that conversion. Just really quickly, let me just show you a quick note here. Let me get rid of this stuff. Just kind of bringing in our properties. Let's rewrite this as using our quotient rule. So wouldn't that be the same as 1 over the natural log of 1 minus the natural log of 2? And the natural log of 1 we know is 0, so then I'm left with minus the natural log of 2. So I could have just done 1 over the negative natural log of 2, which would get me that same negative 1.44. Or just do the natural log of 1/2. So I'm just enlightening you a little bit. All right, here we go. Last one. This one you definitely are going to need your calculator for. It says the data below represents the price and quantity demand for a personal computer. Use a graphing utility to draw a scatter plot. So get your calculator out. If you remember from class yesterday, how do we create a list? I'm going to hit that stat and hit enter. Clear out what is there. Clear, clear. Okay, so I'm going to input all of the prices under list 1. So 2,400, type the numbers in correctly. 2,100, 1,800, 1,600, 1,400. 1,300, 1,100, oops, not 11, 1,100. And then L2, my demand quantity, 160, 166, 173, 178, 182, 193. Okay, so hopefully you have all of those in there correctly in, I guess I can get, oops, I'm going to get rid of my L3 and L4 so it's not so confusing. Get lots of lists in here from my stats class. Let's clear those out. Okay, so once I have my lists in there under L1 and L2, how do we use our graphing utility to make a scatter plot? Well, how do we do a scatter plot? Oops, back. If you hit second and your y equals button, you're going to get up here to this stat plot screen. So then what you can do is you can go into plot 1. If it's off, turn it to on. And then you've got a whole bunch of options here. The first one is your scatter plot. And then it's going to ask you to pick where your lists are. So I want my x variables to be in list 1. My y variables are from list 2. And then what I'm going to want to do is I'm going to go to zoom. And if you go down to number 9, it's a zoom stat. And the reason why we want that is because we're creating a stat plot, a statistical plot of data. And what's the calculator will then move your window to fit whatever it is we're trying to look at. So there is my graph. Not quite straight. There definitely is some curvage there, some little bit crazy curvage. So now what we're going to do is we're going to fit a logarithmic function to that data. So I'm going to hit second mode to quit out. I'm going to go back to stat, go over to calculate. And if you guys remember what we picked yesterday. Yesterday we picked log, or what are we doing? A logarithmic, I think is what we want, right? So a natural log, I think, is our only option. We don't have anything that's just a log, or oh, I guess we have logistic. Yep, nope, we don't want that because it's not regression. So number 9, it's going to say, well, what lists are we using? 1 and 2. You can store your regression line, I think. I think you can store it. Let's see, can I store it under Y1? Nope, I don't know. All right, ignore that. Ignore that. Let's just keep that blank. There is a way to store it. I have to remember how to do that. Maybe you guys can figure that out. Okay, so there is my natural log regression equation. And then if I wanted to graph that, I could type that in. Like, there was a way to get it in there. But I don't remember how to get it in there. So what was it? It was 569.754 minus 53.907 natural log of x. So now when I go back to that graph, you can kind of see the curve fitting your data. And so what your calculator does is it comes up with the best logistic or logarithmic function that fits your data. Okay, so let's go. Fit our logarithmic function. So what did we come up with? Y is equal to 569.754 minus 53.907 natural log of x. So now using that function for part B, I'm just going to do my work up there in A. Can you find the number of personal computers that would be demanded if the price was $1,500? So we're going to plug 1,500 in for x, right? So 569.754 minus 53.907 natural log of 15. Nope. Our y, yep, nope. Our x. Yeah, our x is our price, right? Yes, 1,500. So then the cool thing is, once I have this in my calculator, those who love technology, I can do a trace, and I can type in, oops, nope, it's not going to let me do that, is it? Trace. Why is it not letting me trace? Graph, trace. Oh, because it's only going to let me do it within there. Okay, plot once. I got to move to plot. Yep, hit the up arrow to get to the actual line. That was the problem. So 1,500. Then there it gives me my output, right? 175.52023, which I would have gotten that if I would have just typed all that stuff into my calculator. So we get about 175.5, which we would then round to about 176 computers for your part B. This is your part B answer. Okay. All right. That concludes your notes, everyone.